Welcome back. We are now going to talk about the absolute luminosity of stars, and I'm going to focus on the mass-luminosity relation. Absolute luminosity of a star is basically a measure of how bright it is, how much energy it puts out in all the different electromagnetic spectrums. So pretty much its power output. Okay. The mass-luminosity relation says that the absolute luminosity of a star is proportional to its mass to the power 3.5. And when you look at the Hertzsprung-Russell diagram, the Hertzsprung-Russell diagram is a very important diagram in astronomy. And basically, the Hertzsprung-Russell diagram is a plot of luminosity, the absolute luminosity of stars, versus their temperatures. Okay? And usually we plot the coldest stars on the right side. So let's say something like 2,500 Kelvin. That's probably about the lowest temperature stars, all the way ranging to about 50,000 Kelvin. So those are the hottest stars. So you would anticipate that the coldest stars are going to be not very luminous. They're going to be dim. So they will be plotted down here on the HR diagram. And then as you get hotter and hotter, those will be more luminous stars. So the pattern will be more or less like this. Okay? So the hotter the star is, the more luminous it is. Now it is also true that the hot and luminous stars are also massive. So we can kind of say that as you go up, the mass of the star increases. Okay? So this is known as what is known as the main sequence, and we give this Roman numeral 5. So stars with a spectral classification of Roman numeral 5 are known as main sequence stars. Main sequence. And that means these stars are still living. They haven't started their death process, right? This equation, the mass-luminosity relation, holds only for the main sequence stars. Only for main sequence stars. Now, one of the things we learn in astronomy as when a star begins to die, it starts to get bigger and bigger and bigger and becomes more luminous. It becomes really huge, and it also generally becomes colder. So it moves off the main sequence and it becomes a red giant star. And notice it's becoming brighter and brighter. It's heading upward and it's becoming colder. So it's becoming colder, it's moving this way. So if a star is here, it's becoming colder. It's becoming colder. And possibly it's also becoming brighter, is rising. Okay? So generally speaking, they go through certain stages like this. And they die when they're at that corner of the HR diagram. Low and medium mass stars, when they die, they become planetary nebulae. And high mass stars go supernova. They explode. Those are the ones on this top, okay? They explode in what's known as a type 2 supernova explosion. And then they end up, the remaining core of the star ends up somewhere in this area as a white dwarf star or a neutron star, okay? So anyway, as we're moving off the main sequence, the mass of the star is not changing, it's staying the same, but the luminosity is. It's getting brighter and brighter and brighter. So that's why I said this equation holds only for the main sequence, okay? So it turns out that when you put the mass of the sun, if we use the mass of the sun and we get the actual equation, it turns out that the luminosity of the sun comes out to be about 3.26 times 10 to the 26 watts. Roughly around there, okay? So what we do is we call this luminosity 1, okay? 1 luminosity of the sun, and we plot over here 1, right? And therefore, on the HR diagram, wherever the 1 goes over there, we put the sun, right? And then, what is the surface temperature of the sun? We go down, the surface temperature of the sun is 5,800 Kelvin. Okay? So the sun meets at the intersection of one luminosity of sun, and 5800 Kelvin. So the sun is not the coldest star, not the hottest star, not the brightest star, not the dimmest star. Okay? So if I want to know, let's say there is a star which is 4 times heavier, M is 4, where would that go on the HR diagram? What would its luminosity be? Luminosity is proportional to 4 to the power 3.5. So what would that be? 4 cubed times 4 to the power 1/2. One of the ways you can consider this is you can separate the 3, separate the 0.5, and do them separately. 4 cubed is 64. 4.5 power is like saying square root, so that's like 2. So what would that be? 128. Okay, so what we would do on the HR diagram, we would say, okay, any star that's 10 times heavier than the sun goes over here on the 10. Any star that's 100 times heavier than the sun goes over here. Any star that's 1,000 times heavier goes over here. And then we can keep going up. 10,000, 100,000, and then 1,000,000. Million is about the top that you can get. So when you complete this HR diagram, we actually go all the way up to the top. Okay? All the way up to the top, and all of this area is filled up. Right? So where would this star go? 128, a little bit about above 100. So it's likely to be somewhere in this area on the HR diagram. Okay? This star that is 4 times heavier is likely to be sort of in that area. Notice where the sun is, so it is brighter than the sun. Okay? Well, how about if star that is heavier? Let's go kind of heavier. Let's say the mass is 10 times as much. The luminosity would be 10 to the power 3.5, which is 10 to the third times 10 to the square root. Well, 10 square root is not a perfect number. 10 to the third is 1,000. 10 square root, roughly speaking, about 3. So I'm just going to say approximately. That's 3,000. Okay, 3,000 goes where? Well, that's above 1,000. So now we're talking in this area. Okay? Now we're up higher. So how high can I keep going? Well, it turns out that ordinarily stars can get about 30, 40, 50, 60, maybe up to about 100 times heavier than the sun. But ordinarily, 50 is about the maximum. Okay? So, but it could get even heavier. So let's say for the sake of argument, they can get as heavy as 50. 50. Well, now we're going to have to raise 50 to the power 3.5, which is 50 cubed times 50 square root. Okay? Well, 50 cubed is going to be 5 times 5 times 5. That's 125. 125, and then add 3 zeros. 125,000. 50 square root is roughly about a 7. Okay? So 7 times 125,000, well, 7 times, that's 700,000 times, that's roughly about 875,000. 875,000. If we wanted to get the exact number, we could get our calculator. And we could say 50 to the power 3.5. And we would actually get the exact number, and it would be 883,000. 883,883. Well, that actually comes out to roughly about 1 million. So we're talking about the super giant, huge stars. These are huge, big, main sequence stars. They haven't started dying yet. So they're basically in this corner of the HR diagram, right? How about the most minimum? These are called blue giants. As they go off the main sequence, they're gonna start becoming yellow giants and then red supergiants. They're gonna get even bigger, okay? It turns out that you could also draw the size of the stars in slanted lines like this, okay? So as we're going towards that direction, we're getting bigger and bigger and bigger. So this could be maybe 1,000th the size of the sun, 100th, 1/10th, and then the line that goes through where the sun is, any star on that line is about the same size as the sun, and then 10 times, 100 times, 1,000 times, and 10,000 times. So those would be the really, really, really big stars in the top right corner, okay? So what would be the mass of the low part of the HR diagram? Well, it turns out that the lowest mass possible star is roughly about 8% of the mass of the sun, okay? Sun. Any lower than that, and the star doesn't become a full-fledged star. It becomes what's known as a brown dwarf star, okay? The brown dwarf stars do not have enough mass to undergo the regular proton-proton chain that a main sequence star can have. So if we wanted to know its luminosity, all we would have to put here is the 0.08. All I need to know is the ratio of that star's mass to the sun's mass. So the luminosity would equal proportional, so 0.08 to the power 3.5. So if you go 0.08 to the power 3.5, you get 1.45 times 10 to the minus 4. So roughly speaking, what we can do is you can say this is 10 to the minus 1. Those are stars 1/10 the brightness of the sun. This is 10 to the minus 2. Those are stars 100th the brightness of the sun. And then 10 to the minus 3 and 10 to the minus 4. Okay? So 1,000th the brightness of the sun, 1/10,000th the brightness of the sun. So roughly speaking, these low mass stars will be about 1/10,000th as bright as the sun. The other way you can say it is the sun will be 10,000 times brighter than those stars. And they will be they will go in this corner of the HR diagram, and the universe is very populous with those stars. Those are called red dwarf stars. And in the next video, you will see that those stars live a very, very long time. It takes them billions of years to die. So the universe is populous with them because they haven't even died yet. Okay? So they have a very long lifetime. These stars have a very short lifetime. They die very quickly. The sun's lifetime is pretty long, but not as long as the red dwarfs. Okay? So now you can kind of see the picture of the HR diagram. What does that mean? How to plot stars? What does the Mass-Luminosity relation mean? And how to use it? Okay? Hope that helps. Thank you.